30 times farther from the Sun than Earth, in a region so cold that nitrogen freezes solid and methane falls as snow, there is a planet that by every reasonable expectation should be completely, utterly still. The Sun, from that distance, is barely a bright point. It delivers almost nothing, 900 times less energy than it sends to Earth. By any logic that applies to weather, to atmosphere, to the movement of air across a planetary surface, Neptune should be dead, frozen, featureless, a pale blue marble sitting motionless at the edge of the solar system, too cold and too dark to do much of anything at all. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Instead, Neptune holds the fastest winds ever recorded on any planet in the solar system. Not the fastest winds among the outer planets, the fastest winds anywhere, over 2,000 kilometers per hour, faster than sound, faster than anything Earth's most violent hurricanes have ever produced by a factor of 10. Storms the size of entire continents spin through its atmosphere and then vanish within years, replaced almost immediately by new ones. The planet radiates more than twice the energy it receives from the Sun. Its cloud tops sit near -218 degrees Celsius, making them among the coldest places in the known solar system, while its core burns at temperatures that rival the surface of the Sun itself. None of this should be possible. None of it fits the model, and yet every measurement taken of Neptune confirms the same result. The most distant major planet is also the most violent. That contradiction sits at the center of everything this video is going to cover. The wind speed. Its are extraordinary, but they are not actually the strangest part of the story, and understanding why requires going somewhere most planetary science has never bothered to look. To appreciate what Neptune is doing, you need to picture where it actually sits. The solar system is not evenly spaced. The inner planets, Mercury, Venus, Earth, Mars, cluster close to the Sun, packed within roughly 1.5 astronomical units of each other. Then comes the asteroid belt, then Jupiter, and then things begin to stretch. The distances between the outer planets grow enormous, and by the time you reach Neptune, the numbers have become almost meaningless in any human frame of reference. Neptune orbits at approximately 30 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. 30 of those, Neptune sits 4.5 billion kilometers from the star it orbits. If you drove a car at highway speed, without stopping, toward Neptune, you would die of old age before you arrived. Several times over. This distance is not just an interesting number. It changes everything about what Neptune should be. The intensity of sunlight follows what physicists call an inverse square law. Every time you double your distance from a light source, the brightness you receive drops by a factor of 4. Neptune is 30 times farther from the Sun than Earth is. 30 squared is 900. That means Neptune receives approximately 1/900th of the solar energy that reaches Earth. Stand on Neptune's cloud tops and the Sun delivers roughly 1.5 watts per square meter of energy. On Earth, at noon on a clear day, that number is closer to 1,360 watts per square meter. Neptune gets less than 1/4% of what we get. The Sun is still there, still burning, but from Neptune's perspective, it has become something close to irrelevant. The cold this produces is staggering. At Neptune's cloud tops, temperatures hover around -218 degrees Celsius, which is 55 Kelvin above absolute zero. To put that in context, the surface of Mars on a winter night drops to about -125 degrees Celsius. Pluto, At the far edge of the solar system, averages around -225. Neptune's upper atmosphere is only marginally warmer than the surface of Pluto, and Pluto isn't even a planet anymore. This is the kind of cold where nitrogen, a gas that makes up 78% of the air you are breathing right now, freezes solid. It is cold enough that methane, the same compound in natural gas, condenses into crystals and falls as snow. At this temperature, chemistry slows almost to a halt. Reactions that happen easily at room temperature simply stop occurring. The molecules in Neptune's upper atmosphere are barely moving at all by the standards of ordinary matter. Everything about this picture points toward a planet that should be geologically and atmospherically dead. Frozen, featureless, a blue marble drifting through the dark at the edge of the solar system, doing nothing interesting, going nowhere meaningful on any human timescale. And yet, solar energy drives weather. This is not a theory. It is the demonstrated mechanism behind every storm system on every rocky and gaseous world we understand in detail. On Earth, the sun heats the equator more than the poles, creating temperature gradients that drive wind. Remove the sun and Earth's weather stops. Not immediately, but within weeks the atmosphere would cool toward the ground. Circulation would collapse, and the great engine of storms and seasons would simply wind down. The same principle holds for Jupiter and Saturn. Both giant planets receive far less solar energy per square meter than Earth does, but they are enormous, and Jupiter in particular radiates more internal heat than it receives. That internal heat matters, but even on Jupiter, solar input plays a role in structuring the atmospheric bands and setting the thermal gradients that organize the cloud layers. Solar energy is the foundational driver of planetary weather systems. It is the energy source that every model, every textbook, every working theory about planetary atmospheres treats as the primary input. Neptune gets almost none of it. At 30 astronomical units, the sun is not a disk. It does not look like the yellow circle that lights your morning sky or the source of warmth you feel on your skin in summer. From the surface of Neptune, or from what passes for a surface in its upper cloud layers, the sun would appear as a point of light. Exceptionally bright by the standards of the night sky. Brighter than any star you have ever seen, but a point nonetheless. No warmth, no disk. The kind of light that tells you a star exists somewhere in the darkness, but does nothing useful in terms of heating an atmosphere or driving a circulation system. The sun, from Neptune's surface, would look like a very bright star, beautiful, cold, and almost entirely useless as an engine. The numbers, when you first read them, seem like a misprint. 2,100 kilometers per hour. That is the peak wind speed recorded in Neptune's atmosphere. Written another way, that is roughly 1,300 miles per hour, a number that belongs in the description of a jet engine or a military projectile, not a planet's weather. To understand what that figure actually means, you need something to compare it against. Start on Earth. The strongest hurricane winds ever reliably measured on this planet hit around 200 miles per hour. Those storms level buildings. They push storm surges over coastlines. They are among the most destructive events in human experience. When a Category 5 hurricane comes ashore, it is a civilizational event, the kind of thing that reshapes geography and ends lives by the thousands. 200 miles per hour. Hold that number. Now move outward to Jupiter. The Great Red Spot is perhaps the most famous storm in the solar system, a vortex that has been spinning continuously for at least 3.5 centuries. The winds inside it reach around 250 miles per hour, faster than any hurricane on Earth, and it has been running without interruption since before the American Revolution. It is, by any reasonable standard, an extreme storm. Neptune's peak winds are roughly 5 to 6 times faster. Saturn sits between Jupiter and Neptune in terms of atmospheric violence. Its cloud bands move at speeds approaching 1,100 miles per hour in certain regions. That is already more than 5 times what Earth's worst storms can generate. Saturn's winds are extraordinary. Neptune blows past them too, by nearly 200 miles per hour at the peak. When you lay these numbers side by side, Neptune does not fit the scale. Earth, Jupiter, Saturn, they form a rough progression of increasingly violent weather. Then Neptune appears at the end of that list, like a figure with an extra zero accidentally attached. Something has gone wrong with the pattern. Here is what 1,300 miles per hour actually means physically. The speed of sound through Earth's atmosphere at sea level is roughly 767 miles per hour. Neptune's peak winds are moving at approximately 1.6 times that speed. The air itself is traveling faster than sound can propagate through it. This is not a metaphor. This is a description of a genuine physical regime, one where the normal rules of atmospheric fluid dynamics break down and something more violent takes over. When an object moves through air faster than sound, it generates shock waves, sudden, violent compressions, where the pressure changes almost instantaneously. Fighter jets experience this. Bullets experience this. On Neptune, the atmosphere is doing this to itself, to every cloud layer, every particle, every molecule caught in these wind bands, continuously. The air is not just blowing, it is colliding with itself at supersonic speeds and generating compression fronts that travel through the atmosphere in cascades of energy. Consider what winds like this would do on Earth. A Category 5 hurricane at 200 miles per hour doesn't simply damage buildings, it removes them. The walls fail, the roof goes, the structure ceases to exist as a structure and becomes debris moving at hurricane velocity. At 400 miles per hour, reinforced concrete fails. At 700 miles per hour, the aerodynamic forces involved are beyond anything we engineer buildings to resist. At 1,300 miles per hour, the question of structural damage becomes irrelevant. A building placed in those winds would not be damaged. It would be instantaneously converted from a building into a horizontal projectile. The distinction between the object and the wind would briefly cease to exist. This matters not because buildings exist on Neptune, but because it gives you a physical intuition for what these winds represent as a raw force. They are not merely fast. They are operating in a regime where the violence becomes qualitatively different from anything in Earth's atmospheric experience. Now comes the detail that makes this stranger still. These are not the peak gusts of an isolated storm. They are not the reading taken at the eye wall of a short-lived cyclone that formed, intensified, and then dissipated over the course of a week. Neptune's fastest winds exist in organized bands that wrap around the entire planet. Full circumference, unbroken, sustained. At the equator, winds average around 400 meters per second. That is already close to 900 miles per hour, moving in a direction opposite to the planet's own rotation. The planet spins one way, and its equatorial atmosphere screams the other direction at speeds that dwarf anything on Saturn or Jupiter. The polar regions have their own wind regimes, somewhat slower, but still operating well above the maximum speeds ever recorded on Earth. Between these latitude bands, the shear, the friction between regions of air moving at different speeds in different directions, generates its own turbulence on top of all of this. The total picture is a planet completely wrapped in supersonic wind systems, running simultaneously at every latitude, uninterrupted by land or any solid surface that might slow them down. There is no coastline to break the fetch. There is no mountain range to force air upward and dissipate energy. Neptune's atmosphere is a closed fluid system with nothing to interrupt it, and the winds have been running, apparently, for as long as the planet has existed. This is where the paradox becomes sharpest. Weather on Earth is driven by the sun. Sunlight heats the surface unevenly. Warm air rises, cool air moves in to replace it, and the Coriolis effect from Earth's rotation organizes these flows into the weather patterns we live with. The energy budget is clear. Every hurricane, every thunderstorm, every sustained trade wind on this planet can be traced back to solar radiation striking the surface and converting into heat. Jupiter's winds are more powerful, but Jupiter is also a much larger planet, and it receives more solar energy than Neptune does in absolute terms. Saturn's winds are fierce, but Saturn sits less than 10 times Earth's distance from the Sun. These planets have vast amounts of solar input driving their atmospheric circulation. Neptune gets almost none. From Neptune's distance, the Sun delivers roughly 1/900th of the energy per square meter that it delivers to Earth. The solar input at Neptune is a whisper, a faint, cold light that carries almost no thermal energy by the time it crosses 30 astronomical units of space to reach the planet's cloud tops. And yet here we have winds at 1,300 miles per hour, supersonic, sustained, planet-wide, running in bands that have not stopped in recorded observation. Something is generating the energy that drives these winds, and it is not the Sun. The Sun cannot account for this. The physics simply do not work. 1/900th of Earth's solar input cannot produce winds 10 times stronger than Earth's worst storms, 6 times stronger than Jupiter's most famous vortex. The energy has to be coming from somewhere, and that somewhere is not the sky above Neptune. It is something else entirely, something underneath. These are not gusts recorded during a freak storm event. They are the sustained, average winds wrapping around the planet in bands that never stop. Every planet in the solar system receives energy from the Sun and radiates some of it back into space. This is basic planetary physics. Energy arrives, energy leaves, and the balance between those two numbers tells you something fundamental about what a planet is doing internally. For most planets, the numbers roughly match. But Neptune does something that, when you first see it in the data, looks like an error. Neptune radiates 2.61 times more energy than it receives from the Sun. Not a little more, not a rounding difference. More than twice the energy arriving from our star leaves Neptune as heat. Something inside that planet is generating power on a scale that dwarfs the contribution of the most distant sunlight it receives. The Sun, at 30 astronomical units, is already delivering almost nothing to Neptune's atmosphere, and Neptune is somehow doubling it on the way out. To understand why this is strange, consider what it means in practical terms. Every storm you saw described in the previous section, every supersonic wind band, every atmospheric band wrapping the planet, is being driven by energy that does not come from the Sun. It comes from inside Neptune itself. The planet is not heating from above. It is heating from below. Neptune is running on its own fuel. Now here is where the story gets genuinely unsettling. Uranus exists. Uranus is an ice giant almost identical in size to Neptune. It formed from similar material in a similar region of the early solar system, under similar conditions. It sits closer to the Sun than Neptune, so it receives more solar energy. And Uranus radiates almost exactly what it receives, a ratio of about 1.1 to 1, essentially nothing. Whatever internal heat Uranus ever had, it is not releasing it. The planet is, in thermal terms, almost completely dead. Two near-identical planets. One is the most violent atmosphere in the solar system. One is one of the blandest. The difference between them appears to be this internal heat source, and nobody fully understands why one has it and the other doesn't. The leading theory for Neptune's internal heat is called gravitational contraction. When a planet forms, vast quantities of gas and dust and ice collapse inward under their own gravity. That collapse converts gravitational potential energy into heat. The planet arrives at its final size already hot. not from nuclear fusion the way a star would be, but from the simple mechanical process of everything falling inward and compressing. For a planet as massive as Neptune, roughly 17 times the mass of Earth, that initial heat reservoir would have been enormous. The idea is that Neptune has been slowly radiating this primordial heat outward ever since, a thermal afterglow from the violence of its own formation 4.5 billion years ago. This is a reasonable explanation. It is the kind of explanation that satisfies the basic physics. The problem is that it does not fully hold up under scrutiny. At the rate Neptune is currently radiating heat, models suggest the primordial formation energy should have been substantially depleted by now. The planet should have cooled more, yet it hasn't. There may be additional mechanisms at work. Chemical differentiation, for example, where denser materials slowly sink toward the core, converting gravitational energy into heat as they do, or radioactive decay in the rocky core contributing a smaller additional source. But these additions are difficult to quantify and even harder to confirm without a mission in orbit around Neptune collecting detailed data. What makes the Uranus comparison so maddening is that it strips away the easy answers one by one. You cannot simply say massive planets retain heat longer because Uranus is essentially the same mass and it hasn't. You cannot say internal composition is the explanation because the two planets have nearly identical compositions as far as we can measure from a distance. The most widely considered hypothesis at the moment is that Uranus suffered a large oblique impact at some point in its early history, one that created a thermally stable stratification layer somewhere in its interior. This layer would act as a lid, trapping heat below it and preventing it from convecting upward to the atmosphere. Uranus's internal heat is still there, potentially, just locked beneath a thermal barrier it cannot penetrate. Neptune, under this hypothesis, escaped that particular accident, or its own formation history produced different interior conditions. Without that lid, Neptune's heat moves freely through its interior and drives the temperature gradients that ultimately produce everything happening in the clouds above. The supersonic winds, the massive storm systems, the relentless atmospheric violence, all of it traces back to heat rising from the deep interior through thousands of kilometers of supercritical fluid, ultimately reaching the cloud layer with enough energy to throw gas into motion at speeds no other planet in the solar system can match. There is something almost counterintuitive about this picture when you hold it next to what Neptune looks like in photographs. The planet is a deep, tranquil blue. It looks cold and still, the way you would expect something 4 billion kilometers from the sun to look. The surface temperature at the cloud tops is around -218 degrees Celsius, among the coldest atmospheric readings anywhere in the known solar system. Nothing about the visual impression suggests an internal furnace, yet underneath that frozen surface, the core temperature is estimated at roughly 5,400 Kelvin. That is comparable to the surface temperature of the Sun. Neptune presents one face to the universe, serene, blue, distant, and conceals something radically different at its center. What this means for the wind speeds discussed before is that the previous section's numbers are not just extreme, they are powered by something deep and ancient. The energy driving a wind moving at 1.6 times the speed of sound has been stored inside Neptune since the planet formed. It is not borrowed from a star. It is not generated by tidal forces or recent geological activity. It is, as best as current science can determine, primordial energy that has been slowly bleeding outward through the planet's body for nearly 5 billion years, and doing so efficiently enough to keep the atmosphere in a permanent state of violent motion. The mystery of Neptune's internal heat is not a minor puzzle at the edges of planetary science. It sits at the center of why Neptune is what it is. Answer the heat question and you answer the wind question. You answer the storm question. You answer why the coldest planet by surface temperature is simultaneously the most violent planet by any atmospheric measure. The heat is the engine and the winds are the exhaust, but the engine itself remains poorly understood. Gravitational contraction gets you most of the way there and then leaves a gap. The gap isn't large enough to invalidate the theory, but it is large enough to matter, and that gap widens dramatically when you look at Uranus sitting next door, essentially identical in every measurable property, generating none of the same output. How Neptune has maintained this internal furnace for 4.5 billion years, while its nearly identical twin next door went cold, is a question planetary science has not fully answered. When Voyager 2 reached Neptune in August of 1989, it found something nobody was fully prepared for. The spacecraft had already completed flybys of Jupiter, Saturn, and Uranus. By the time it arrived at Neptune, the scientific teams had been running for 12 years. They had calibrated their expectations on what Voyager 2 found at Uranus 3 years earlier. A cold, largely featureless world with almost nothing happening in its atmosphere. Neptune, they assumed, would be similar. It was farther away. It received even less sunlight. The logic seemed sound. What the cameras sent back instead was a dark, enormous oval sitting in Neptune's deep blue atmosphere like a bruise the size of a planet. And it was spinning. The feature was called the Great Dark Spot. Its dimensions were approximately 13,000 kilometers by 6,600 kilometers. To put that in terms that mean something, the diameter of Earth is about 12,700 kilometers. This storm was roughly the same size as the entire planet you are standing on, a vortex large enough to swallow the Earth whole, rotating in an atmosphere so cold the cloud tops sit at negative 218 degrees Celsius, on a planet powered by an internal furnace rather than sunlight. The numbers were difficult to process when they arrived. They are still difficult to process now. Jupiter's Great Red Spot is the storm that most people reach for as a point of comparison. It is famous. It is old. It has been sitting in Jupiter's southern hemisphere for at least 350 years. But the Great Red Spot, while larger in raw size, produces winds of roughly 400 to 600 kilometers per hour at its outer edges. The Great Dark Spot on Neptune was measured at around 2,100 kilometers per hour. That is more than 3 times faster. The winds surrounding Neptune's storm were not just extreme by the standards of planetary science. They were supersonic. The air itself was moving faster than sound could travel through it. Around the edge of this single storm system, shockwaves were running continuously. Not occasionally. Continuously. The speed of these winds was particularly baffling because Neptune receives less than 1% of the sunlight that Earth does. Solar heating should be minimal, yet the winds were the most violent ever recorded in the solar system, operating under conditions where there is almost no external energy input to drive them. This meant that the energy powering Neptune's storms had to come from somewhere else, from beneath the cloud layers, from the planet's interior, from heat generated by gravitational compression and radioactive decay at the core. The storm was not being blown around by sunlight. It was being powered from within. The appearance of the storm was striking in ways that went beyond its size. Against Neptune's vivid blue, the Great Dark Spot stood out as a sharp, dark oval, its edges clearly defined by the enormous pressure differential between its interior and the surrounding atmosphere. But hovering directly above the storm were bright white clouds, brilliant and sharp, composed of frozen methane ice crystals condensed at extremely high altitudes. These companion clouds were not decorative. They were casting shadows falling downward onto other cloud layers 56 kilometers below them. That single detail tells you something important about the vertical scale of what was happening. Cloud structures on Neptune extend through enough altitude that sunlight can enter at an angle, strike a high cloud, and project a shadow onto a completely different layer of atmosphere more than 50 kilometers beneath it. The storm was not just wide, it was deep. Why does a dark spot look dark? The answer is not immediately obvious. Neptune's atmosphere is primarily hydrogen and helium, with a thin layer of methane that gives the planet its blue color by absorbing red wavelengths of light. When a dark spot forms, it is not that something dark is sitting on the surface. What appears to be happening is that the storm creates a region where the upper atmosphere is disturbed, where haze layers are pushed downward or cleared away, exposing darker material beneath. Deeper in Neptune's atmosphere, where pressure is higher and the chemistry is different, the coloring agents change. The dark oval is essentially a window. The storm is pulling aside the upper layers and revealing something in the depths below, a dark eye looking upward through its own clouds. What lay in those depths was still unknown. Neptune's extreme conditions made it impossible for any probe to descend very far into its atmosphere. The planet has no solid surface for a lander to rest upon. Any probe sinking into Neptune would simply keep sinking, descending through layers of increasing pressure and temperature until its instruments failed. What the dark spot revealed was a glimpse into a realm that remained fundamentally inaccessible. A layer of Neptune's interior that no spacecraft had ever sampled directly, and likely no spacecraft ever would. The storm was a diagnostic tool, revealing information about the invisible workings of the planet's atmosphere through its own structure and behavior. The Great Dark Spot was not sitting still. Astronomers tracking its position over the course of Voyager 2's observations found that it was drifting toward the equator at a rate of about 1.2 degrees of latitude per month. That sounds modest. It is not. The forces required to push a storm system the size of Earth laterally across an atmosphere at that rate are substantial. Whatever pressure gradients and wind shear interactions were acting on this storm, they were doing so continuously and at scale. The Great Dark Spot was not anchored. It was moving, carried by forces operating across the entire planetary atmosphere. Sit with the scale of this for a moment. This is a storm rotating at supersonic speed. It is the diameter of Earth. It is embedded in an atmosphere where the average wind speeds across the entire planet already exceed anything ever recorded in Earth's history. The storm did not stand out because the rest of Neptune's atmosphere was calm. It stood out even against a backdrop of winds routinely exceeding 1,000 kilometers per hour. That is what Neptune looked like to Voyager 2 when it arrived. Not a quiet frozen world at the edge of the solar system. A blue planet in active, violent, large-scale atmospheric motion, with a continent-sized vortex embedded in its middle latitudes and supersonic winds surrounding it on all sides. The white companion clouds drew particular attention from researchers. These were not storm clouds in the terrestrial sense. They were formed at altitudes so high and temperatures so extreme that methane gas froze into ice crystals, the same process that produces high cirrus clouds on Earth, but operating with different chemistry and at far more savage temperatures. The shadows those clouds cast onto the layers below were one of the most unexpected details in the Voyager 2 imagery. It meant the cloud structure above the Great Dark Spot extended vertically over a distance comparable to the cruising altitude of a commercial aircraft, stacked multiple times over, all of it in violent motion. There was a secondary storm system visible in the same 1989 observations, a smaller bright feature that moved faster than anything else in Neptune's atmosphere. It lapped other features entirely as it orbited the planet. Researchers called it the Scooter. Its relationship to the Great Dark Spot is not fully understood, but its presence confirmed that the Great Dark Spot was not the only violent feature in Neptune's atmosphere at the time. It was simply the largest and most dramatic. The planet was hosting multiple simultaneous storm systems of different scales and speeds, all operating within an atmosphere that had no business being as energetic as it was given the amount of sunlight reaching that far from the sun. The fact that multiple storm systems coexisted in Neptune's atmosphere simultaneously challenged earlier assumptions about how planetary weather systems operate. On Earth, storm systems are transient. Hurricanes last days or weeks. Even the longest-lived terrestrial storms eventually dissipate. Jupiter's Great Red Spot had endured for centuries, suggesting that under certain conditions, planetary storms could persist for extended periods. But Neptune appeared to host not one long-term storm, but several, all moving at different speeds, all coexisting within a continuous environment of extreme winds. This suggested that Neptune's atmospheric conditions somehow favored the formation and maintenance of multiple simultaneous storm systems, in a way that was unusual even by the standards of the other gas giants. What Voyager 2 captured during its Neptune encounter was the first and, to this day, still the closest look anyone has ever taken at this storm, or at any storm on Neptune. The Great Dark Spot was documented in detail across those few dozen hours of close approach. Its size was measured, its wind speeds were recorded, its structure was photographed. Researchers had every reason to believe that this storm, like Jupiter's Great Red Spot, was a long-term feature of Neptune's atmosphere, something that would still be there whenever a follow-up mission eventually arrived. 5 years after Voyager 2 captured this image of a continent-sized vortex spinning at supersonic speed, the Hubble Space Telescope looked at the same spot in Neptune's atmosphere and found nothing there at all. The disappearance of the Great Dark Spot was, in some ways, more disturbing than its appearance. When Voyager 2 photographed that continent-sized vortex in 1989, scientists were startled by its scale and violence. But a storm of that magnitude existing on a distant, frigid world could at least be filed under the category of surprising. What happened next was something else entirely. When the Hubble Space Telescope turned toward Neptune in 1994, 5 years after Voyager 2's flyby, the Great Dark Spot was simply gone. No remnant, no weakened spiral of cloud, nothing where a vortex the size of Earth had been spinning at supersonic speed half a decade earlier. That is not how storms are supposed to behave. That is not how anything that large is supposed to behave. On Jupiter, the Great Red Spot has been spinning continuously since at least the 1660s. Astronomers in the 17th century wrote down observations of a persistent oval feature on Jupiter's southern hemisphere, and it is still there today. More than 3.5 centuries of uninterrupted rotation, the storm has shrunk over time. It was once large enough to swallow 3 Earths side by side, and now it fits roughly 1. But it has never dissolved, never vanished between observation sessions. The reason comes down to the structure of Jupiter's atmosphere, which is organized into stable, locked bands of alternating wind that essentially trap and anchor large vortex systems. Those bands act like walls. Once a storm establishes itself within them, the surrounding structure holds it in place, feeds it, keeps it coherent across centuries. Neptune has no such structure, or rather, it has something that looks like banded structure from a distance, but behaves in a fundamentally different way underneath. The forces holding Neptune's atmospheric bands together are not stable anchors. They are temporary balances between competing pressures, and those balances break. When they do, whatever storm was sitting within that system goes with them. The leading explanation for what Neptune's dark spots actually are involves a process called an anticyclone. In an anticyclone, atmospheric pressure builds in a localized region, and air descends rather than rising. On Earth, high-pressure systems bring clear skies for the same reason. Descending air suppresses cloud formation. On Neptune, the equivalent process is thought to clear away the upper haze layers, revealing the darker, deeper atmosphere below and producing the characteristic dark oval shape. The storm isn't truly a storm in the way we usually think about storms. It's more like a hole, a region where the usual cloud cover is suppressed by descending air, creating a window into a lower atmospheric layer that absorbs more light. What you're seeing when you look at a dark spot on Neptune is, in a sense, an absence, a clearing. Maintaining that clearing requires a precise balance of forces. The anticyclonic pressure must remain high enough to keep suppressing the surrounding atmosphere, while the edges of the system must hold against the surrounding winds trying to tear it apart. On Neptune, with winds moving at speeds that have no comparison elsewhere in the solar system, that balance is genuinely difficult to sustain. The margins are narrow. When the system finally loses coherence, when the forces maintaining it shift just enough, the surrounding atmosphere rushes back in, clouds reform, and the dark patch fills in and disappears. The whole process, from formation to dissolution, can apparently happen within a few years. Scientists have now tracked 6 dark spots on Neptune since 1989. Voyager 2 found 2 during its flyby. Hubble, since its launch in 1990, has identified 4 more. Each observation campaign reveals a Neptune that looks different from the one seen before. The original Great Dark Spot gone in 1994. A new one, this time in the northern hemisphere, appearing in its place. Another forming years later, tracked for a while, then fading. The planet is not cycling through stable states. It is continuously generating and destroying massive storm systems on timescales of a few years, never settling, never organizing itself into anything permanent. There was another feature Voyager 2 recorded in 1989 that captured attention for a different reason. Smaller than the Great Dark Spot, a bright, compact cloud feature, nicknamed the Scooter, moved across Neptune's atmosphere at a speed that outpaced everything else around it. While the Great Dark Spot drifted slowly and the surrounding cloud bands moved at their own rates, the Scooter was lapping them. It circled the planet faster than the storms above it and the atmospheric bands beside it, an independent feature racing through a system already in constant motion. What caused the Scooter to move so differently from the features surrounding it was not fully resolved before it too faded from observation. But its existence pointed to the same underlying reality. Neptune's atmosphere is not a single system moving in concert. It is a collection of features operating at different speeds and different altitudes, all of them temporary, all of them in motion relative to each other. The existence of multiple distinct features operating independently pointed to something remarkable about Neptune's atmosphere. Rather than being a unified system where all components moved together, Neptune exhibited atmospheric fragmentation, different regions responding to different pressure gradients and wind patterns simultaneously. This fragmentation appeared to be a fundamental characteristic of how the planet's atmosphere organized itself. Each feature existed within its own local dynamic, influenced by, but not fully controlled by the broader atmospheric circulation patterns surrounding it. This independence of motion revealed deep truths about Neptune's internal structure and the forces at work within its turbulent skies. This is the key difference that separates Neptune from Jupiter at a fundamental level. Jupiter's atmosphere, for all its dramatic appearance, is organized. It has lasting structure. Neptune's atmosphere is organized only briefly, locally, and never for long. Each dark spot is less a fixture of the planet and more an event within it, something that the atmosphere generates, sustains for a while, and then absorbs back into itself. The violence is not just in the wind speeds, it is in the instability, in the refusal of any large-scale structure to hold. What this cycling behavior reveals about Neptune's underlying energy state is significant. Storms on Earth form when conditions are right and dissipate when those conditions change. The energy that drives them, heat, pressure differentials, moisture, eventually redistributes, the gradients flatten, and the storm runs out of fuel. Neptune's atmosphere is apparently never running out of fuel. New dark spots replace old ones with a consistency that suggests the energy driving them is continuous and substantial. The internal heat engine powering Neptune's winds is not providing just enough energy to sustain a single persistent storm. The way a calm ocean might support one isolated eddy, It is providing enough energy to continuously rebuild massive vortices from scratch after each one dissolves, over and over, across timescales we have only observed the beginning of. Neptune apparently spends more than half its time hosting at least one of these enormous vortices, cycling through them the way a restless ocean cycles through wave patterns, never fully still, never fully the same. Neptune is not a solid body, and this matters more than it might seem. When we talk about a planet rotating, we usually picture something simple, a sphere turning on an axis, the way a basketball spins. Every point on the surface completes one rotation in the same amount of time. That is how solid objects work. Neptune does not work that way. Nothing about Neptune works that way. Because Neptune has no surface in the meaningful sense, different parts of its atmosphere are free to rotate at entirely different speeds. And on Neptune, they do, by a margin that has no equivalent anywhere else in the solar system. Here is how scientists establish what Neptune's rotation actually is. Since the atmosphere itself moves at inconsistent speeds, you cannot use cloud patterns as a reference. What you can use is the magnetic field. Neptune's magnetic field is generated deep inside the planet, anchored to the interior rather than the atmosphere above it. That field rotates with the planet's core. Voyager 2 measured it in 1989 and found a rotation period of 16.1 hours. That number, 16.1 hours, is the closest thing Neptune has to a true rotational period. It is the heartbeat of the planet's interior. Now look at what the atmosphere does. At Neptune's equator, the cloud bands take roughly 18 hours to complete one rotation. That is nearly 2 full hours slower than the interior beneath them. The equatorial atmosphere is lagging. It is dragging behind the planet's own core, falling further back with every orbit, like a runner who cannot keep pace with the track itself moving under their feet. At the poles, something entirely different is happening. The polar atmosphere rotates in about 12 hours, 4 hours faster than the interior. The poles are racing ahead of the planet's own core, lapping the equatorial regions with every few rotations. Stop and sit with that for a moment. The equatorial atmosphere and the polar atmosphere are not just moving at different speeds. Relative to the interior, they are moving in opposite directions. The equator falls behind. The poles push forward. Between them, there are transition zones where these opposing circulation regimes meet. And in those zones, two enormous masses of atmosphere are grinding against each other at continental scale. Place your hands flat on a table. Press them down firmly. Now slide your right hand towards you and your left hand away from you simultaneously. The point between them, the line where friction concentrates, is where the stress builds. That is where material tears. That is where energy releases. That is what is happening across entire latitude bands on Neptune, continuously, across a planet 4 times the width of Earth. This phenomenon has a name: differential rotation. Every gas planet in the solar system shows some version of it. Jupiter rotates faster at its equator than at its poles. Saturn does the same. But on Jupiter and Saturn, the difference is measured in minutes, a relatively modest offset between equatorial and polar rotation rates. On Neptune, the difference between the fastest and slowest regions of the atmosphere is roughly 6 hours. No other planet in the solar system comes close to that number. The question is why Neptune's differential rotation is so extreme. The answer connects directly to something that has come up before: Neptune's internal heat. The temperature gradient between Neptune's superheated core and its frozen cloud tops is enormous, and that gradient does not apply uniformly across latitude. The poles receive different solar input than the equator, and Neptune's own internal heat reaches the surface unevenly through the convective churning of its interior. These variations in thermal energy set up profoundly different circulation patterns at different latitudes. Near the equator, where the dynamics favor one kind of thermal flow, The atmosphere develops a slow, lagging rotation. Near the poles, where the thermal structure drives a different regime entirely, the atmosphere spins fast. The internal heat engine is not just powering the winds, it is setting them spinning at different rates across different parts of the planet, creating the conditions for the shear zones that follow. Most of Neptune's winds at lower latitudes blow retrograde. That means they flow in the direction opposite to the planet's rotation. You are standing, in effect, watching the atmosphere move backward against the spin of the world beneath it. At higher latitudes, the winds flip to prograde, moving in the same direction as the planet's rotation. The boundary between these two flow regimes, the latitude zone, where retrograde gives way to prograde, is where wind shear reaches its maximum intensity. Two air masses moving in fundamentally opposite directions, pressing against each other across thousands of kilometers of atmospheric boundary. On Earth, wind shear is a well-understood danger. Pilots avoid it. Meteorologists track it carefully. A region where winds at different altitudes are moving in different directions will tear a developing storm cell apart, or feed it catastrophically, depending on geometry. The shear zones on Neptune are not measured in tens of kilometers. They are measured in tens of thousands. The atmospheric masses involved are not weather systems. They are hemisphere-scale circulation regimes. The turbulence and pressure differentials generated along these boundaries are what seed Neptune's storm systems, the dark spots, the vortices, the violent convective eruptions that characterize the planet's atmosphere. This is not a self-correcting system. There is no mechanism by which Neptune's differential rotation gradually smooths itself out and stabilizes. The internal heat that creates the temperature gradients responsible for the different circulation regimes continues to flow upward from the core. The equatorial and polar atmospheres continue spinning at their mismatched rates. The shear zones continue grinding. The storms they generate continue forming, spinning up to full violence, and eventually dissolving, only to be replaced by new ones fed by the same unresolved mechanical stress. Other gas giants have differential rotation and produce storms. Jupiter's Great Red Spot is the most famous example in the solar system, but Jupiter's atmosphere, for all its violence, operates within a narrower band of differential rotation. Neptune's atmosphere operates across a range so extreme that it produces retrograde flow at one latitude and prograde flow at another, with the transition zone between them acting as a permanent engine for atmospheric chaos. The friction point between these opposing flows is one of the most mechanically violent environments in the solar system, and it never stops. The temperature at Neptune's cloud tops, -218 degrees Celsius, is one of the coldest numbers you can attach to a planetary atmosphere anywhere in the known solar system. That is 55 Kelvin. 55 degrees above absolute zero, the theoretical point at which all molecular motion stops entirely. To put that in terms that means something physically, nitrogen, the gas that makes up 78% of Earth's air, freezes solid at -196 degrees Celsius. Neptune's cloud tops are colder than that. Methane, which we think of as a gas, falls as snow in Neptune's upper atmosphere. At 55 Kelvin, even the chemistry of familiar molecules starts behaving in ways that have no counterpart in everyday experience. This is the planet in the photographs, that deep, almost artificial blue, serene, cold, still looking. The visual impression is of something frozen and quiet, a marble left at the edge of the solar system, too far from any warmth to do anything interesting. That impression is completely wrong, but it starts with a number that is genuinely extreme. No major planetary atmosphere in our solar system gets colder than this. Pluto, during parts of its highly elliptical orbit, can approach comparable surface temperatures. But Pluto is no longer classified as a major planet, and its atmosphere is a thin, barely there haze. Neptune's cloud tops represent deep, sustained cold across a body 24,000 kilometers in radius, blanketing a world in a frozen shell that looks, from a distance, like perfect stillness. Now go deeper. Not far, in astronomical terms, but deep enough that the temperature stops dropping and starts climbing. Below the cloud layers, pressure increases rapidly, the atmosphere thickens, and the temperature begins to reverse. By the time you've descended through the outer atmosphere and into the transitional layers beneath, you're no longer in the realm of freezing cold. You're in something else entirely. The numbers climb steadily as depth increases, driven by compression and by the heat rising from below. This is where the planet stops looking like the photographs. At Neptune's core, the temperature is approximately 5,400 Kelvin. That number deserves a moment. The surface of the Sun, the photosphere, the bright disk you see in the sky, sits at roughly 5,778 Kelvin. Neptune's core is nearly as hot as the surface of a star. A planet sitting 4.4 billion kilometers from the Sun, in a region where sunlight arrives at 1/900th of its strength at Earth, is carrying an interior temperature that rivals the face of the nearest star in the sky. Something is generating that heat from within, and it has been doing so for 4.5 billion years. The temperature differential between Neptune's cloud tops and its core is roughly 5,345 Kelvin, across approximately 24,000 kilometers. To understand why that number matters, consider Earth for comparison. The temperature difference between Earth's surface and the base of the crust, the deepest layer of solid rock beneath our feet, is around 700 degrees Celsius. That gradient spans about 50 kilometers. Neptune achieves a temperature jump 7.5 times greater than Earth's crustal gradient, but spread across a distance 480 times larger. What this creates, physically, is a convective engine of extraordinary power. Hot material at the core wants to rise. Cold material at the cloud tops wants to sink. The entire interior of the planet becomes a circulation system, carrying heat upward through thousands of kilometers of supercritical fluid and gas, driving currents that never stop. Convection itself is not unusual. Earth's mantle convects. The Sun convects. Every system with a heat source at the bottom and a cold layer at the top will develop circulation if the temperature gradient is steep enough. What makes Neptune remarkable is the scale and the intensity of that gradient, combined with the fact that it's being maintained internally rather than by an external source. The convective circulation inside Neptune isn't driven by sunlight. It's driven by whatever process is keeping that core at 5,400 Kelvin after billions of years of slow cooling. That circulation is what reaches the atmosphere. The violent differential rotation covered earlier, the winds moving in opposing directions at different latitudes, the storm systems forming and dissolving. These are surface expressions of energy that originates 24,000 kilometers below. The weather you would experience at Neptune's cloud tops is powered by heat rising from a depth that on Earth would place you past the core and out the other. Side. Think about what that means structurally. A storm on Earth draws energy from sunlight heating the surface, from temperature differences between equatorial and polar regions, from the heat stored in oceans. The engine is shallow. It operates over the top few dozen kilometers of the atmosphere at most. Neptune's engine runs through the entire body of the planet. The connection between the deep interior and the upper atmosphere is not metaphorical. It is a direct convective pathway, heat physically moving upward through thousands of kilometers and eventually manifesting as motion at the cloud tops. The supersonic winds are not simply an atmospheric phenomenon. They are the visible output of a planetary furnace. What makes this contrast so striking and worth holding in mind is how completely the photographs mislead you. Neptune looks cold because its surface is cold. That deep blue color, Those white methane clouds drifting across its face. Nothing about the visual impression suggests a body running an internal temperature close to 5,400 Kelvin. Yet the cold exterior and the hot interior are not in contradiction. They are the two ends of the same engine. The cloud tops are cold precisely because they are radiating energy away into space, energy that arrived there from the interior, carried upward by convection, finally released at the surface as the heat that ultimately drives Neptune's wind. The coldest atmosphere in the solar system and a core as hot as a stellar surface are not opposites. One is the consequence of the other. The violent blue surface of Neptune is, in a very real sense, the exhaust of an internal engine running at temperatures that rival the surface of the Sun. 7,000 kilometers below Neptune's cloud tops, something is happening that sounds like it belongs in a physics thought experiment rather than in an actual planet. The temperature extremes discussed a moment ago, a frozen outer atmosphere and a core running at stellar surface temperatures, create more than just convective winds. They create a pressure and heat environment so extreme that the molecules making up Neptune's interior stop behaving like molecules at all. And the most dramatic example of this involves one of the simplest organic compounds in the known universe, methane. Methane is CH4, one carbon atom bonded to 4 hydrogen atoms. It is stable, common, and unremarkable under the conditions you encounter in everyday life. It is the primary component of natural gas. It burns cleanly. It condenses into ice at around -182 degrees Celsius, which is cold by human standards but routine for the outer solar system. At the top of Neptune's atmosphere, methane freezes into the bright cirrus clouds that form the planet's visible cloud deck. It is, under normal conditions, one of the quietest molecules in chemistry. 7,000 kilometers below those clouds, there are no normal conditions. Pressures at that depth run into the millions of atmospheres. Temperatures climb into the thousands of degrees. Under those conditions, the bond between carbon and hydrogen, the bond that makes methane stable, that holds the molecule together, simply breaks. The hydrogen atoms scatter into the surrounding fluid. The carbon atoms are left free. Free carbon atoms under millions of atmospheres of pressure do not stay free for long. Carbon has a very specific preference when it finds itself under extreme compression. It forms diamond, not graphite, not amorphous carbon, not any of the softer crystal structures that carbon adopts at lower pressures. Under sufficient compression, carbon locks itself into the tightest, most ordered lattice it can produce. The hardest natural substance in chemistry precipitates out of the fluid interior of Neptune and begins to fall. This is diamond rain, and it may be happening right now, continuously, in the deep interior of the planet. The scale of this is worth sitting with. The diamonds forming under these conditions are not the microscopic specks you might initially imagine. Some models suggest that individual diamond crystals could grow to substantial sizes as they descend through thousands of kilometers of supercritical fluid toward the rocky core. They fall not through open space, but through a pressurized ocean of water, ammonia and methane in states that have no real analogy on Earth's surface. Matter that is simultaneously liquid and gas, dense and flowing, electrically conductive and chemically reactive. Through this ocean, diamonds sink. The question of whether this was actually happening inside Neptune, or whether it was an elegant theoretical possibility that nature had declined to use, was not purely academic. Researchers decided to test it. The problem is obvious. Nobody can drill 7,000 kilometers into a planet 4 billion kilometers away. So scientists brought the conditions to Earth instead. Using high-powered lasers, researchers at institutions including Lawrence Livermore National Laboratory created brief, localized conditions of extreme pressure and temperature in laboratory samples of hydrocarbon compounds similar to what exists inside Neptune. The laser pulses generated pressures millions of times greater than Earth's atmospheric pressure and temperatures of thousands of degrees. held for fractions of a second. When they analyzed the results, they found exactly what the models had predicted. Diamond structures formed. Carbon atoms released from their molecular bonds had organized themselves into crystalline lattices under the extreme compression. The experiment confirmed that diamond precipitation is not just theoretically plausible, it is the natural outcome of the physics operating inside ice giants. What makes this particularly striking is the implication about what is accumulating at Neptune's core over geological time. Neptune is roughly 4.5 billion years old. If diamond rain has been falling through its interior for even a fraction of that time, the build-up around the core would be extraordinary. Some researchers have proposed that the core of Neptune may be surrounded by a layer of diamond, building up incrementally over billions of years, crystal by crystal, in absolute darkness at pressures that no instrument humans have ever built could survive. The hardest natural substance known to chemistry, forming not in geological veins or volcanic pipes as it does on Earth, but precipitating out of a hot fluid ocean in the interior of a distant ice giant. There is nothing in Earth's experience that maps onto this directly. Diamond on Earth forms in the mantle at pressures of around 45,000 to 60,000 atmospheres over millions of years and is brought to the surface by violent volcanic eruptions. Diamond inside Neptune forms at pressures potentially hundreds of times greater than that, falls through fluid rather than rock, and has nowhere to go. It simply accumulates. The violence of Neptune, which is obvious and measurable at the cloud tops, turns out to extend all the way down into its chemistry. The atmosphere is violent in the sense that its winds exceed the speed of sound, and its storms swallow areas the size of planets. But the interior is violent in a quieter, stranger way. It is transmuting the molecules it is made of. It is breaking apart stable compounds and rebuilding their components into exotic crystalline structures. It is chemically remaking itself, continuously, under conditions that have no parallel anywhere in everyday experience. This chemical violence is invisible from Earth. No telescope captures diamond formation in an interior 7,000 kilometers below a cloud deck 4 billion kilometers away. What astronomers see from Earth is the blue disk, the bright companion clouds, the occasional dark storm system drifting across latitudes. The interior is entirely hidden. The exotic physics happening down there is inferred from models, confirmed by laser experiments in laboratories, and extrapolated from what we understand about the behavior of matter under extreme conditions. That extrapolation points to something almost difficult to hold in mind. Right now, while Neptune sits at the edge of the solar system in the dark, while no spacecraft is anywhere near it and no instrument is measuring it directly, methane molecules are being torn apart by pressure and heat in its deep interior. Carbon atoms freed from those bonds are crystallizing into diamond, and those diamonds are falling, slowly, through thousands of kilometers of supercritical fluid toward a core that may already be ringed with the accumulated deposits of billions of years of this same process. Inside Neptune right now, diamonds may be falling through a hot ocean of supercritical fluid, and nobody on Earth has any way to see it directly. Below Neptune's churning cloud layers, the familiar categories of matter, solid, liquid, gas, stop being useful descriptions. What exists there has no clean name in everyday language. Scientists call it a supercritical fluid, which is a technical term for something that behaves like a liquid in some ways, and like a gas in others, and which refuses to commit to either. This is not a metaphor or an approximation. It is a genuine state of matter that emerges when pressure and temperature climb beyond a certain threshold, and the molecular forces that normally separate one phase from another simply break down. Water boils at 100 degrees Celsius at sea level because the atmosphere pressing down on it is relatively weak. Push the pressure high enough while raising the temperature and water rear, aches a point where the boundary between liquid and vapor disappears entirely. There is no surface. There is no boiling. The substance just exists, dense and hot and moving, all at once. The critical point for water occurs at 374 degrees Celsius and 22 megapascals, where the distinction between liquid and gas fundamentally ceases to exist as a meaningful category. Neptune's interior conditions vastly exceed these thresholds, creating a supercritical state of extreme density and temperature existing simultaneously. Scientists must rely on laboratory experiments and mathematical models to understand these conditions, since direct observation remains impossible. The behavior predicted by these models reveals a realm of physics distant from everyday experience, one that challenges intuition at every level. These predictions, however, have become increasingly sophisticated as computing power has expanded. Inside Neptune, this is not an edge case. It is the dominant condition across most of the planet's volume. Below the visible atmosphere, the planet transitions through a layer of hydrogen and helium gas that grades over thousands of kilometers into a vast interior region made primarily of water, ammonia, and methane in these supercritical states. Scientists sometimes call this the mantle or the icy layer, though neither term fully captures what it is. The word icy is particularly misleading. Under normal solar system conditions, water and ammonia would indeed be frozen solids at Neptune's distance from the Sun. But normal conditions don't exist inside Neptune. The temperatures there run into the thousands of degrees. The pressures crush inward with a force roughly 100,000 times greater than the atmospheric pressure at sea level on Earth. At 10 gigapascals, the numbers become almost abstract. The weight of the material above pressing down on every square centimeter is staggering. Nothing about those conditions is cold, and nothing about them is solid. What that pressure does to matter is worth sitting with for a moment. On Earth, molecules in a gas are spaced far apart, moving freely, bouncing off each other only occasionally. Molecules in a liquid are packed closely enough that they interact constantly, but still flow around each other. At the pressures inside Neptune's mantle, even that distinction collapses. Molecules are forced into configurations where they interact continuously, where they cannot freely separate like a gas, but also cannot lock into the ordered structures of a solid. They are simultaneously constrained and mobile. If you could somehow hold a sample of Neptune's interior material in your hand, which you could not for reasons that should be obvious, it would not look like water or ice or steam. It would not look like anything you have ever seen. This matters for more than theoretical reasons. That supercritical fluid layer carries electricity. Water and ammonia under these conditions become highly conductive, meaning charged particles can move through them freely, the way they move through a wire. This electrical conductivity is almost certainly the source of Neptune's magnetic field. Deep inside the planet, this conductive fluid churns in convective currents driven by the heat rising from the core. And those moving currents generate a magnetic field the way any moving electrical charge generates one. The geometry of that field, tilted nearly 47 degrees from Neptune's rotational axis, offset dramatically from the planet's center, reflects the irregular asymmetric pattern of flow inside the supercritical layer. The magnetic field is strange because the interior that generates it is strange. But the role of this layer goes beyond magnetism. It is the primary channel through which heat moves from Neptune's scorching core toward the cold outer atmosphere. The core sits at roughly 5,400 Kelvin. The cloud tops register around 55 Kelvin. Something has to carry that enormous difference across 24,000 kilometers of planetary interior. And that something is the churning motion of this supercritical fluid. Hot material at depth is less dense, so it rises. Cooler material from above sinks, The cycle repeats continuously, carrying thermal energy upward through the planet, the way water in a heated pot eventually begins to circulate. Except on Neptune, the pot is the size of a planet. The temperature differential rivals the surface of the Sun, and the fluid conducting the heat exists in a state that has no counterpart in a kitchen or a lab. Oratory on Earth. This convective engine is the link that connects the exotic interior physics to the violent atmosphere we observe from the outside. The supersonic winds at the cloud tops, the massive dark spots, the storm systems that dwarf entire planets. None of it would be possible without the constant upward delivery of heat from the interior. Neptune's atmosphere is not generating its own energy from thin air. It is the exhaust of something happening much deeper, something massive and continuous and poorly understood, playing out in a region of the planet that no instrument has ever directly sampled. Everything visible about Neptune is downstream of this process. The winds are downstream. The storms are downstream. The entire surface expression of Neptune's violence traces back to convection currents moving through a layer of matter that shouldn't exist, operating under pressures that have no equivalent anywhere in human experience. This ocean of matter that is simultaneously liquid and gas is the hidden machinery behind everything happening in the atmosphere above it. Neptune's color, that impossible saturated blue that shows up in photographs and looks almost artificial, comes from a gas that makes up barely 1% of its atmosphere. That gas is methane, and the way methane produces that color is straightforward enough. It absorbs red wavelengths of sunlight and lets blue wavelengths bounce back out into space. Sunlight enters Neptune's atmosphere carrying the full visible spectrum. The red end gets swallowed. What escapes is blue. The result is a planet that looks, in photographs, less like a real world and more like something rendered by a computer that was told to make something visually striking. But the color is real, and the molecule responsible for it is doing far more than filtering light. Neptune's atmosphere is roughly 80% hydrogen and 19% helium. Those two gases, in terms of pure volume, dominate everything, but hydrogen and helium are essentially transparent. They don't do much optically. Methane, at 1 to 2%, is the minority constituent that controls what the planet looks like from the outside. It is a small fraction producing an outsized effect, and that pattern, a minor ingredient driving major consequences, turns out to describe methane's role in Neptune's dynamics as well, not just its appearance. The cloud structure, built from this atmosphere, is not a single layer, it is a stack. At the very top, at temperatures around -235 degrees Celsius, methane gas freezes into ice crystals and forms high-altitude clouds. These clouds are thin and wispy, resembling cirrus clouds on Earth, and they sit at extraordinary altitudes above the rest of the atmospheric structure. What revealed their height most dramatically was a shadow. These high methane clouds cast shadows on lower cloud layers 56 kilometers beneath them. 56 kilometers of vertical separation. On Earth, the highest cirrus clouds sit maybe 12 kilometers above sea level. Neptune's uppermost clouds tower more than 4 times higher above the layers below them, and the atmospheric architecture in between is not empty. It is turbulent, layered, and active across that entire vertical range. Below the methane ice layer, the atmosphere continues to build in complexity. Deeper down, where temperatures and pressures rise, clouds of ammonia and hydrogen sulfide are believed to form. Deeper still, at pressures around 50 times Earth's sea level atmospheric pressure, there are likely water ice clouds. These layers don't just sit inertly on top of each other. Each layer has its own temperature, its own composition, and its own circulation regime. Air rising from warmer depths carries heat upward. Cooler material descends. These vertical movements don't respect boundaries. They punch through layer after layer, mixing chemistry and energy across dozens of kilometers of atmosphere simultaneously. The result is a three-dimensional weather system, not a flat one. Storm systems on Neptune are not just wide, they are deep. Then there is the haze. High above even the methane ice clouds, Neptune's upper atmosphere carries a persistent layer of photochemical smog, ultraviolet radiation from the sun. Faint as it is at Neptune's distance, still has enough energy to break apart methane molecules. When methane gets shattered by UV light, the fragments recombine into heavier hydrocarbon compounds. Those compounds don't dissipate. They accumulate as fine aerosol particles, forming a hazy layer that sits at the very top of the atmosphere. This is essentially the same chemistry that produces smog over large cities on Earth, running on a planetary scale, powered by light that has traveled 4.4 billion kilometers and arrived barely strong enough to register. The fact that Neptune generates a photochemical haze at all, given how little solar energy reaches it, is itself a small indicator of how much the rules that govern quieter planets don't straightforwardly apply here. The photochemical haze and methane ice clouds below it interact continuously throughout Neptune's atmospheric column. Aerosol particles gradually settle and mix with methane ice crystals, creating a transitional zone where different chemical regimes meet and blend. This mixing is persistent. Ultraviolet radiation constantly generates new aerosol particles at the top, while gravitational settling draws older particles downward into progressively denser regions. The result is a vertical chemical gradient that complements the physical gradients of temperature and pressure already present. These interconnected gradients, thermal, chemical, and compositional, create instabilities and driving forces that propagate throughout the entire atmospheric structure. The atmosphere is not simply stacked in S. Apparent layers but dynamically coupled, with processes at the top responding to conditions below and vice versa. What this layered architecture produces in terms of weather is not easy to picture from the outside. Think of the atmosphere not as a shell but as a deep, churning volume. Warm, convective currents rising from below drive material upward through the hydrogen-helium gas, through the water clouds, through the ammonia and sulfide layers, all the way up toward the frozen methane cirrus at the top. Cold material cascades back down. The vertical distance over which this convection operates spans tens of kilometers. The horizontal winds wrapping around the planet at supersonic speeds are fed partly by this vertical circulation, heat arriving at the upper layers from below, creating pressure gradients, accelerating flow. The storm systems and dark spots that form and dissolve across Neptune's face are not separate phenomena from the cloud chemistry. They emerge from it. Methane sits at the center of this. It marks the top of the vertical column with its ice clouds. It provides the visual contrast that makes storms visible as bright white features against the blue. It produces the haze layer above. And critically, methane is an absorber of infrared radiation. Even at the concentrations present in Neptune's atmosphere, methane traps heat. It affects where in the atmosphere energy accumulates. It shapes the thermal gradients that drive convection. Remove methane from Neptune's atmosphere and you would change the color, yes, but you would also alter the thermal structure that organizes the entire convective engine underneath it. The molecule that makes Neptune beautiful is also one of the key ingredients in the thermodynamic engine that makes it violent. Uranus and Neptune formed from essentially the same raw material, in essentially the same region of the early solar system, and ended up being almost the same size, same class of object, same general composition, same broad neighborhood in the outer solar system. By almost every metric that planetary scientists use to categorize worlds, these two should be near twins in behavior. What Voyager 2 found when it visited them 3 years apart remains one of the most unsettling discrepancies in the history of planetary exploration. Uranus came first. In January of 1986, Voyager 2 made its closest approach, and scientists leaned in, expecting something. They got almost nothing. The atmosphere was bland, featureless. A pale blue-green disk with no visible storms, no dramatic cloud structures, no dark spots, no obvious wind bands of the kind that stripe Jupiter and Saturn. The most dramatic thing about Uranus from an atmospheric standpoint was how undramatic it was. Researchers had traveled 12 years in anticipation of that flyby, and the planet gave them very little to work with. 3 years later, at Neptune, the same spacecraft found the fastest winds ever recorded on any planet. A storm the size of Earth, multiple simultaneous weather systems, and an atmosphere in a state of violent, ongoing reorganization. The contrast was jarring. It still is. Here is the raw comparison. Uranus is slightly larger than Neptune. Its equatorial diameter is about 51,000 kilometers against Neptune's 49,500. Uranus orbits closer to the Sun. It receives more solar energy. It is, by the standard logic of planetary science, the one that should be more active. Instead, Uranus's atmosphere sits inert, while Neptune tears itself apart with supersonic winds. Something is deeply wrong with the straightforward picture. Or rather, something happened to one of these planets that didn't happen to the other, and that event set them on completely different paths for the next 4 billion years. The key number is the internal heat ratio. Neptune radiates roughly 2.6 times more energy than it receives from the Sun. This excess is heat escaping from the planet's interior, driving convection, feeding temperature gradients, powering the atmosphere from below. Uranus radiates essentially no excess heat at all. It takes in solar energy and sends back almost exactly the same amount. Whatever internal heat Uranus generated during its formation, it is not reaching the surface. It is locked somewhere inside the planet, unable to escape. Without that convective heat flow, there is no engine. The atmosphere has nothing to run on beyond the thin trickle of sunlight arriving from a star 2.7 billion kilometers away. That trickle is not enough to build supersonic winds. On Neptune, the internal furnace makes up the difference. On Uranus, something appears to have sealed the furnace shut. The leading hypothesis involves a collision. Early in the solar system's history, during the era when planets were still assembling and the orbital architecture was chaotic, Uranus is thought to have been struck by a large object, something roughly the size of Earth or larger. This impact knocked Uranus onto its side, giving it its famous 98-degree axial tilt. But the hypothesis goes further than that. The impact may have done something to the internal structure of the planet. Specifically, it may have created a stable layer of stratification deep inside Uranus, a kind of thermal barrier where denser material sits beneath lighter material in a configuration that resists mixing. On Earth, when warm air sits below cold air, you get convection. The warm air rises, the cold air sinks, and the system circulates. But if somehow the layering ends up thermally stable, denser and cooler material at the top, less dense and hotter material trapped below, the circulation stops. The heat has nowhere to go. It stays locked at depth, unable to reach the surface, unable to drive any atmospheric activity above it. This is what may have happened inside Uranus. The ancient impact reshuffled the interior into a configuration that has been quietly suppressing convection for the last 4 billion years. Neptune, under this picture, either never experienced such an impact or experienced one whose effects were different. Its interior was left in a state that allows heat to convect freely upward through thousands of kilometers of supercritical fluid, feeding the temperature differentials that ultimately drive everything you see at the cloud tops. The storms, the winds, the dark spots forming and dissolving on timescales of years, All of it traces back to whether the internal heat can escape. On Neptune, it can. On Uranus, it apparently cannot. This is a compelling hypothesis. It also remains exactly that. No spacecraft has returned to either planet since 1989. The data available from Voyager 2's 2 brief flybys, combined with decades of ground-based and Hubble observations, is not enough to verify the internal structure of either planet with the precision needed to confirm this picture. Scientists can measure what comes out of the atmosphere. They cannot easily see what is happening 10,000 kilometers below it. The stratification hypothesis fits the observations, but so do several competing ideas. Some researchers have proposed that Uranus and Neptune may have different ratios of rock to ice in their interiors, and that this compositional difference could account for the divergence in heat output. Others have explored whether the distribution of heavier elements in the mantle could create the necessary thermal barriers without requiring an impact at all. A Uranus orbiter mission is currently in planning stages, with a potential launch in the early 2030s under NASA's planetary science priorities. That mission, if it launches, would give scientists their first detailed look at Uranus in nearly 5 decades and might begin to constrain what is actually happening inside the planet. Neptune, as of now, has no dedicated follow-up mission in development. The planet that is actually doing something extraordinary, the one with the supersonic winds and the cycling storms and the internal heat source, remains scheduled for no return visit. The closest we may get to new Neptune data in the near term will come from indirect observations and atmospheric modeling, neither of which can substitute for a spacecraft in orbit. What makes the Uranus-Neptune problem so important extends beyond the two planets themselves. Ice giants, as a category, appear to be among the most common types of planets in the galaxy. When astronomers catalogue exoplanet detections, a large fraction of the confirmed planets fall into a size class roughly corresponding to ice giants. What we learn about the physics of Neptune and Uranus, about how internal heat escapes or gets trapped, about what determines whether an ice giant becomes atmospherically violent or dormant, has implications for interpreting thousands of worlds orbiting other stars. The single variable that separates Neptune from Uranus, whatever it turns out to be, may also explain why some exoplanets in this size class show atmospheric signatures of intense activity, while others remain cold and quiet. Two planets nearly identical at birth, separated by a single variable we still do not fully understand, and one of them became the most violent atmosphere in the solar system, while the other went completely quiet. On August 25, 1989, a spacecraft the size of a small car, traveling at 60,000 kilometers per hour, made its closest approach to Neptune after 12 years of flight through interstellar space. Voyager 2 had not been built specifically for Neptune. It had been built for Jupiter. The rest of its journey was made possible by something that doesn't happen often, a rare alignment of the outer planets that allowed a single spacecraft, using each planet's gravity as a slingshot, to visit 4 worlds in a single continuous trajectory. Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989. The alignment that made this grand tour possible recurs roughly once every 175 years. The engineers who designed the mission knew that. They built a spacecraft capable of lasting long enough to use it. By the time Voyager 2 crossed into Neptune's neighborhood, it had been flying for 4,388 days. Its plutonium power source was slowly decaying. Its instruments had survived the radiation belts of Jupiter, the icy debris fields of Saturn, and the cold emptiness of the outer solar system. The team operating it from Earth was communicating across a distance so vast that even radio signals, traveling at the speed of light, took over 4 hours to make the one-way trip. A command sent from Pasadena in the morning wouldn't reach the spacecraft until the afternoon. A response wouldn't arrive until evening. There was no real-time control. Everything Voyager 2 did at Neptune, it did on pre-programmed instructions decided weeks in advance. The expectations going in were not high. 3 years earlier, Voyager 2 had flown past Uranus and found essentially nothing dramatic. A smooth, faintly banded atmosphere. No major storms, no violent features. Scientists had largely assumed that Neptune, being even colder and even farther from the Sun, would look similar. The two planets were close enough in size and presumed composition that Uranus had become the working template. Neptune would be bland. Neptune would be quiet. The flyby would confirm what everyone already expected. What they found instead redrew the picture entirely. The closest approach window, the period during which Voyager 2 was near enough to Neptune to gather meaningful high-resolution data, lasted roughly 37 hours. In those 37 hours, the spacecraft sent back images of a planet nobody had anticipated. There was a massive dark oval near the equator, later named the Great Dark Spot, a vortex roughly the size of Earth, with winds at its edges exceeding 2,100 kilometers per hour. There were multiple smaller storm systems scattered across the atmosphere. There were bright streaks of methane ice cloud casting shadows on lower cloud layers 56 kilometers below them. And the winds. The winds were something no instrument in the history of planetary science had recorded anywhere before. Then came Triton. Neptune's largest moon had been known to exist since 1846, but nobody knew what it looked like up close. When Voyager 2 turned its cameras toward it, the images showed a surface unlike anything in the solar system. Triton orbits Neptune backwards, opposite to the planet's rotation, suggesting it was captured rather than formed in place. Its surface temperature measured around -235 degrees Celsius, making it one of the coldest objects ever directly observed. And then, on the surface, geysers. Nitrogen geysers, erupting through the ice and sending dark plumes several kilometers into the thin atmosphere before the wind carried them downrange. A captured moon, orbiting the wrong way, with active geysers on a surface nearly 240 degrees below zero. In a single flyby, Neptune had produced two of the most unexpected discoveries in the history of outer solar system exploration. The scientists in the control room at NASA's Jet Propulsion Laboratory did not hide their reaction. By any reasonable measure, the Uranus flyby 3 years earlier had been a professional success, but a dramatic disappointment. Uranus gave them data. Neptune gave them a revelation. The project scientist for the Voyager program, Ed Stone, described what the team was seeing as something that fundamentally changed the understanding of how ice giants could behave. The cold in the distance, they had assumed, should produce stillness. What Neptune showed instead was that distance from the Sun and atmospheric violence had almost nothing to do with each other. Neptune had effectively dismantled the model the moment Voyager 2 arrived. Here is what makes those 37 hours strange to sit with now. They were not a beginning. They were everything. Voyager 2 did not settle into orbit. It did not slow down and circle back. It passed through at 60,000 kilometers per hour and kept going. The window opened, the images poured in, and then the window closed as the spacecraft continued outward. Today, Voyager 2 is in interstellar space, beyond the heliopause, traveling in a direction away from Neptune. It will never return. No other mission has gone in its place. In the 35 years since that flyby, astronomers have observed Neptune from Earth-based telescopes and from the Hubble Space Telescope. Hubble discovered that the Great Dark Spot was gone by 1994 and that new storms had appeared. Ground-based instruments have tracked changes in cloud coverage over decades, but none of this is the same as being there. Earth-based observation of Neptune is like trying to study the details of a painting from half a kilometer away. Voyager 2's images remain, By an enormous margin, the sharpest and most detailed data ever gathered about what Neptune's atmosphere actually looks like at close range. The contrast with other planets is striking. Jupiter has been visited by the Galileo orbiter, which spent 8 years studying it in detail. Saturn hosted the Cassini mission for 13 years. Mars currently has active orbiters and surface rovers. Neptune has had one visitor, once, for 37 hours in 1989. There are mission proposals. Scientists have been advocating for a Neptune orbiter for years, and some concepts have reached early planning stages, but no mission has been approved and funded and launched. The earliest realistic arrival date for any new spacecraft would be sometime in the 2040s, assuming a mission launched in the next several years. That would mean Neptune's atmosphere going unvisited for more than half a century between Voyager 2's departure and any new arrival. Everything we know about the Great Dark Spot came from 37 hours of data. Everything we know about Neptune's wind speeds at close range came from those same 37 hours. Every high-resolution image of Neptune's storms, every wind speed measurement, every piece of data about what the atmosphere actually looks like up close was captured during those 37 hours, and nothing has been sent back since. Neptune has seasons for the same reason Earth does. It orbits the Sun at an axial tilt, currently 28.3 degrees, that is almost identical to Earth's. That similarity ends almost immediately when you start looking at the timescales involved. On Earth, a season lasts 3 months. On Neptune, a single season lasts approximately 40 Earth years. One full Neptunian year, spring, summer, autumn, winter, and back again, takes 165 Earth years to complete. Neptune was discovered in 1846. It did not finish its first complete orbit since that discovery until 2011. The entire span of modern observational astronomy, from the invention of the telescope to the present day, does not add up to a single Neptunian year. This creates a measurement problem that is almost impossible to overstate. Every long-term study of Neptune's climate is working with an incomplete dataset by definition. Modern instruments capable of detailed atmospheric observation have existed for roughly 80 years. That covers less than 2 full Neptunian seasons. Trying to understand Neptune's full seasonal cycle from the data we currently have is something like trying to reconstruct the pattern of Earth's climate. By observing only January and February, you are seeing a fraction of the picture, and you cannot be entirely sure which fraction it is. What astronomers have seen despite these limitations is genuinely striking. Starting in the 1980s, observations showed that Neptune's southern hemisphere was getting brighter. Cloud band sizes increased. The overall reflectivity of the southern hemisphere climbed measurably over the course of decades. This was consistent with what you would expect from an approaching southern summer solstice. More direct sunlight hitting the southern pole as Neptune moved through that portion of its orbit. The changes were slow, unfolding over years, but they were real and they were measurable. Something was responding to the seasonal geometry, even at 30 times Earth's distance from the Sun. The energy involved is almost nothing by Earth standards. Neptune receives roughly 1/900th of the solar radiation that Earth does. The Sun from Neptune is not a disk. It is a point of intense light, brighter than any star in our sky, but nowhere near the dominant heat source it is here. The seasonal changes driven by this faint, distant light are subtle in absolute terms, but Neptune is not operating at Earth conditions. Its atmosphere is already at extreme temperatures, already churning with supersonic winds, already powered primarily by internal heat rather than sunlight. Even a small shift in the solar angle hitting a given hemisphere is enough to nudge that system. The atmospheric response to Neptune's faint seasonal signal, measured over decades, tells scientists that the planet is sen. sensitive in ways they are still working to quantify. Here is where the timescale problem bites hardest. Some of the patterns researchers have observed in Neptune's atmosphere, cycles of brightening, changes in storm frequency, shifts in cloud distribution, could be genuine long-term climate dynamics unrelated to seasons, or they could be seasonal effects operating on 40-year timescales that look like independent cycles when you only have 80 years of data to examine. Separating these two possibilities requires observations that span multiple full seasons. No researcher alive today will collect those observations personally. The dataset needed to resolve these questions will be assembled by scientists who have not yet been born, drawing on work done by people who are currently in graduate school. There is something almost philosophically uncomfortable about this. The tools of modern science are extraordinarily powerful. Space telescopes, ground-based observatories, computational models that can simulate planetary atmospheres in fine detail. And yet the fundamental constraint on understanding Neptune's seasonal dynamics is simply time, not technology, not funding, not the difficulty of the physics. Time. Neptune moves too slowly for human lifetimes to capture its full behavior. The planet does not care about the length of a human career. What this means practically is that every interpretation of long-term trends in Neptune's atmosphere carries an asterisk. The brightening observed in the southern hemisphere over several decades may be summer arriving. It may be something else entirely that happens to look like a seasonal effect when viewed through an 80-year window. Distinguishing between these possibilities requires patience, measured not in years but in generations. The 1980s observations that first detected the brightening trend were made by researchers who retired without seeing the trend reverse. Their successors are watching for the reversal now. Whether they will see it before they retire is genuinely uncertain. A researcher who dedicated an entire career to watching Neptune's seasons would retire before they had seen even half of one. Neptune's magnetic field is tilted 47 degrees from the planet's rotational axis. That number requires a moment to absorb. On Earth, the magnetic poles sit reasonably close to the geographic poles. A compass needle points roughly north because Earth's internal magnetic dynamo is roughly aligned with the axis the planet spins around. The same is true for Jupiter. The same is true for Saturn. For most planets we have studied in any detail, the magnetic field and the rotational axis live in rough agreement. Neptune threw that expectation out entirely. 47 degrees is not a small discrepancy. It is not the kind of thing you explain away as measurement error or minor wobble. Picture a planet spinning on its axis, and then picture its magnetic field tilted so far off that its poles sit not near the top and bottom of the planet, but somewhere near the equator. That is Neptune. If you were standing on the surface trying to navigate by compass, the needle would be pointing sideways. The magnetic north of Neptune is roughly where its equatorial regions are. Nothing about that is normal, but the tilt is only half of the strangeness. Neptune's magnetic field is also offset from the planet's center by about 0.55 Neptune radii. That figure deserves unpacking. Neptune's radius is roughly 24,600 kilometers. An offset of 0.55 radii means the center of the magnetic field is displaced from the planet's physical center by more than 13,000 kilometers. It is not anchored in the middle of the planet. It sits more than halfway toward the surface, somewhere in the interior layers, generating a field that is fundamentally asymmetric. One side of Neptune is wrapped in a far stronger magnetic field than the other. As the planet rotates, the entire magnetic configuration swings through space in a wide, lopsided arc. The result is a magnetosphere that behaves unlike anything around Jupiter or Saturn. Those planets have magnetospheres that are large and roughly organized, predictable structures that channel the solar wind in consistent ways. Neptune's magnetosphere is different every few hours. Because the magnetic axis is so far tilted from the rotational axis, every full rotation of the planet, about 16 hours, sweeps the magnetic poles through a dramatic arc. The solar wind, which is the continuous stream of charged particles flowing outward from the Sun, encounters a completely different magnetic geometry depending on when it arrives. The interaction changes constantly. The magnetosphere stretches, compresses, twists and reforms in a continuous cycle of asymmetric convulsion. Uranus has a similarly tilted and offset magnetic field. That is one of the very few things the two ice giants actually share. Uranus's magnetic field is tilted about 59 degrees from its rotational axis and offset from the center in a comparable way. Scientists noticed this when Voyager 2 flew past Uranus in 1986, and were genuinely confused. When Voyager 2 reached Neptune 3 years later and found the same configuration, the confusion deepened. 2 planets, same bizarre magnetic geometry. Something about ice giant interiors produces this, and the question of what that something is has not been cleanly answered. The leading theory centers on the supercritical fluid layers inside Neptune. Inside Jupiter and Saturn, magnetic fields are generated by metallic hydrogen, a state of hydrogen compressed so severely that its electrons move freely, creating an electrically conductive fluid that acts as a dynamo. The dynamo generates a field roughly aligned with the rotation axis because the metallic hydrogen layer sits deep and symmetrically inside the planet. Neptune has no metallic hydrogen. What it has instead is a thick layer of water, ammonia and methane in a supercritical state, a hot, dense fluid that conducts electricity because of the pressure and temperature conditions acting on it, not because of any metallic phase transition. This supercritical layer sits at a different depth than metallic hydrogen projections, Trojan would, and it is distributed asymmetrically through the interior. The dynamo it creates is a different kind of dynamo, a shallower dynamo, a less symmetric one, and the field it generates reflects that asymmetry directly. The specific geometry, why 47 degrees, why this particular offset, is not something the current models can predict from first principles. Scientists can describe what kind of dynamo would produce a tilted offset field, but they cannot yet run the interior physics of Neptune in enough detail to say exactly why the tilt is what it is. The problem is that nobody has been inside Neptune. Voyager 2 measured the field from the outside during its flyby, giving scientists the shape of the magnetosphere and the basic parameters of the dipole. What generated those parameters, in what layers of the interior, through what specific fluid dynamics, remains a matter of theoretical inference rather than direct measurement. What is clear is that the magnetic field has real consequences for the planet beyond just navigation confusion. Charged particles from the solar wind are captured and accelerated by magnetic fields, forming radiation belts around planets. Earth has the Van Allen belts. Jupiter has intense radiation belts that would be lethal to unshielded electronics within hours. Neptune has radiation belts too, but their structure is wild and complicated by the asymmetric field. Because the field is so tilted, the belts shift dramatically in latitude as the planet rotates. The plasma environment around Neptune is perpetually reorganizing. There is something fitting about this. Neptune surprises at every layer. Its atmosphere is more violent than its solar input can explain. Its storms form and vanish on timescales nothing else in the solar system matches. Its interior synthesizes diamonds and sustains matter in states that have no counterpart in everyday physics. And then, beneath all of that, at the level of its most fundamental physical property, the magnetic field that defines how it sits within the larger solar environment, Neptune is wrong there too, tilted wrong, centered wrong. configured in a way that every well-behaved planet in the solar system would find unrecognizable. The field that should organize Neptune's relationship with the rest of the solar system is instead a lopsided off-center thing that sweeps attically through space with every rotation. Exactly the kind of wild asymmetry you would expect from a planet that refuses to behave. Everything that makes Neptune extreme also makes it a window into things that go far beyond a single distant planet. Every strange thing we have uncovered about Neptune, the internal heat, the supersonic winds, the vanishing storms, the diamond rain, points outward toward larger questions about how planets work and what determines their character. Neptune is not a curiosity sitting at the edge of our solar system. It is an argument, and the argument it makes challenges some of the most basic assumptions built into planetary science. Start with the internal heat. For decades, the working model was straightforward. A planet's weather is driven by the energy it receives from its star. Earth gets a certain amount of solar input, and that input stirs the atmosphere into the weather patterns we experience. Jupiter is farther out, gets less energy, but it's enormous, so its weather is enormous. The logic held. Then you reach Neptune. Neptune receives roughly 1/900th of the solar energy Earth does. By the standard model, it should be essentially inert. Instead, it generates sustained winds faster than the speed of sound. The explanation that Neptune is powered by its own internal heat, radiating out 2.61 times the energy it receives from the sun, breaks the model completely. Solar input is not the controlling variable. Something internal is. And once you accept that, you have to ask the question for every other planet you study. How much of what we are seeing in an atmosphere is driven by the star, and how much is coming from below? This matters enormously for exoplanet science. Astronomers have now confirmed thousands of planets orbiting other stars, and a significant fraction of them fall into the ice giant size range, worlds roughly the mass of Neptune or Uranus. When researchers try to interpret the atmospheric signals coming from these distant worlds, they are using models built on solar system science. If those models underestimate the role of internal heat, the interpretations will be wrong. A planet that looks atmospherically quiet based on its distance from its star might be running a violent internal engine that observations have simply not resolved yet. Neptune forces that question onto every ice giant discovered anywhere. Then there is the Uranus problem. Two planets built from essentially the same ingredients, in essentially the same part of the early solar system, nearly identical in size and mass. One became the most violent atmosphere in the solar system. The other became one of the most featureless. The leading explanation points to a single catastrophic impact early in Uranus's history, a collision that may have created a stable thermal stratification inside the planet, trapping its internal heat and preventing it from convecting upward. Neptune presumably avoided that outcome, or experienced a different one, and its heat flows freely. If that hypothesis is correct, then the character of an entire planet, its weather, its storms, its atmospheric violence, can be determined by a single random collision that happened 4.5 billion years ago. Planetary character is not an inevitable consequence of size and composition. It is set by accidents, by chance. The same planet, struck at a slightly different angle during formation, could have ended up completely different. That is a deeply unsettling thing to absorb. If you are trying to build a general theory of how planets behave, the storms themselves carry a separate implication. Neptune's dark spots form and dissolve over years. Jupiter's great red spot has been spinning for at least 3 centuries and possibly much longer. The comparison makes Jupiter look stable and Neptune look chaotic. But the more important point is what Neptune reveals about atmospheric systems in general. A vortex the size of Earth, with winds exceeding 2,000 kilometers per hour, can simply cease to exist in the span of 5 years. Atmospheric features at extreme scales are not automatically self-sustaining. They require a precise balance of forces, and when that balance shifts, even continental-scale storms can dissolve entirely. The assumption that extreme weather systems are durable because of their size turns out to be wrong. Neptune has been demonstrating this repeatedly since 1989, and we have not fully absorbed what it means for how we model atmospheric stability on other worlds. The interior physics carry implications of a different kind. Diamond rain, supercritical fluids behaving simultaneously like liquid and gas, a magnetic field tilted 47 degrees and offset from the planetary center by more than half the planet's radius. None of this fits the models developed for the better-studied gas giants, Jupiter and Saturn. Those planets run on metallic hydrogen dynamos with magnetic fields that align reasonably close to their rotational axes, with interiors that, while exotic, follow patterns that were anticipated before spacecraft arrived. Neptune's interior is operating on a different set of rules entirely. The supercritical fluid layer, conducting electricity and generating the planet's bizarre magnetic field, represents a class of planetary interior that most models were not designed to describe. And because ice giants appear to be among the most common planet types in the galaxy, what happens inside Neptune is probably happening inside enormous numbers of worlds we will never visit. The physics in that supercritical layer is not a local curiosity. It may be the dominant form of planetary interior in the universe. What makes all of this stranger is the gap between how important Neptune is and how little we have actually seen of it. One spacecraft, one flyby, 37 hours of close observation, 35 years ago. Everything built on top of that, every model, every hypothesis, every inference about how Neptune's interior works or why its storms dissolve or what drives its heat, is built on a dataset that would be considered preliminary for a planet 10 times closer and 100 times easier to reach. The gap between what Neptune reveals and what we actually know about it is enormous. Every answer it has produced has generated at least 2 new questions that the available data cannot resolve. The most violent atmosphere in the solar system is also the least studied, the least visited, and the one whose secrets we have barely begun to pull apart. Right now, 4.4 billion kilometers from where you are sitting, the winds on Neptune are moving faster than the speed of sound. New storm systems are probably forming somewhere in that deep blue atmosphere. Old ones are probably tearing themselves apart. Somewhere 7,000 kilometers below the cloud tops, diamond crystals are falling through hot supercritical fluid in complete darkness. None of it has stopped. None of it is waiting. No spacecraft is currently on its way there. The last mission carrying instruments capable of telling us anything new about Neptune's storms, its interior, its magnetic field, its cycling dark spots. That mission flew past in August of 1989 and has been coasting through interstellar space ever since. Voyager 2 is now roughly 20 billion kilometers from Earth and moving farther away every second. It is not coming back. Nothing has replaced it. The earliest a dedicated Neptune mission could realistically reach the planet, given current planning timelines, is sometime in the 2040s. That is not a guarantee. That is an optimistic projection. Neptune's extreme distance makes orbital missions expensive and time-consuming to plan. Yet the scientific returns would be substantial, given the planet's unusual weather patterns and atmospheric composition. These make it a natural laboratory for understanding planetary atmospheric dynamics. Still, funding and political will for such distant missions continue to fade, so everything happening on Neptune right now is happening without us. The supersonic wind bands wrapping the entire planet, still running. The differential rotation grinding equatorial and polar atmosphere against each other at continental scales, still grinding. Whatever replaced the last great dark spot, still spinning, or already dissolving, and we would have no way to know which. The most violent atmosphere in the solar system is currently operating entirely outside our awareness. In a region of space where our instruments do not reach, and our machines have not returned. There is something worth sitting with in that fact. We have mapped the surface of Mars in extraordinary detail. We have orbiters circling Jupiter and Saturn. We have sent probes into the Sun itself. And Neptune, which turned out to be perhaps the strangest, most energetic, most mechanically extreme planetary body in the entire solar system, has received exactly one visitor for less than 2 days, more than 35 years ago. The blue storm is still spinning, and nobody is watching.